Sounds like this one's on. What Chandra just presented, it does constitute an effects analysis on fish by itself. It's very useful information, and a lot of that was suggested during some of the earlier reviews of some of the earlier drafts of the effects analysis. And so that's why we explored that topic in more detail. This section I'm going to go on to just now is thinking of more specific fish effects, bringing in some of the biology from some of the different studies that have been done in the Delta. One thing to bear in mind with these analyses and the other things that Chandra presented is that a lot of those are modeling assumptions that have facilitated the effects analysis. We would definitely imagine that during BDCP implementation that there would be a lot more real-time management, so that, for example, flows or diversions at the North Delta intakes wouldn't be blindly responding just to flow triggers, but they would also be responding to biological monitoring, for example, of fish coming downstream, as is done at the moment in the current system. So I think that's important to bear in mind as we look at the results of some of these analyses. So I'm focusing on far-field effects, which were mostly outlined in Appendix 5C of the effects analysis. I won't speak to near-field effects, and by near-field effects I really am talking about things that are actually happening pretty much at the intakes themselves, which you can see here on this map taken from the document. Those are discussed in the analysis of entrainment and impingement in Appendix 5B, as well as exploration of predation effects in Appendix 5F, just for your reference. But today I'll go over river flow and survival effects, two broad topics, river flow and survival effects, and then another topic that I'll call entry into channel divergences, and especially the entry into channel divergences really reflects some of the information that Chandra just outlined here. Obviously, the entry into channel divergences, such as Georgiana Slough, is important given the historical observations that survival is generally lower within entry into the interior delta, which is why we have a lot of focus on that particular topic. Is this working okay? I feel like I'm really booming here. No? Okay. Some of the methods that I'll outline are the delta passage model, which is focusing on for Chinook salmon smolts. These are methods for river flow and survival effects. I'll talk about an analysis suggested in previous agency review for spring run and fall run Chinook salmon smolt survival through delta survival, based on the paper by Ken Newman from 2003. I'll also focus on a new analysis looking specifically at survival under different bypass flow levels, the levels that Chandra just outlined. I won't speak to one of the other analyses this morning that we also did on this topic, which is called particle tracking modeling nonlinear regression analysis, but that's also in Appendix 5C. I've tended to, as you've probably seen in these slides, pull things out of the document. It doesn't make for very attractive reading sometimes on these slides, but what I'm trying to do is actually make it clear where the things are coming from. So hopefully you'll get a copy of the presentation and you'll actually be able to see where the different things are coming from. These are a couple of the methods slides from the delta passage model, and it's really just to illustrate that the delta passage model considers through delta survival from the top of the plan area here around about Fremont Weir down to Chips Island. Today we're mostly concerned with, of course, in relation to far field effects of the North Delta intakes, we're interested in the fish that might be coming down this portion here, not so much today with the South Delta portion, although we have looked at that as well as part of the delta passage model. It has several reaches, and there have been modifications as we've been going through the effects analysis. So, for example, this Verona reach here was a fairly new addition. The survival through Yolo bypass has been updated with some of the latest data from UC Davis. But in essence, the Delta Passage model has fairly broad, long reaches to it. So the reach SAC1 here is the reach that would have the North Delta intakes in it. This figure is actually slightly modified from the figure that's in the appendix. I noticed as I was putting this together, a couple of the junctions weren't quite correctly marked. But from about Freeport down to the junction with Sutter and Steamboat Slough is the reach SAC1, where the intakes are proposed to be located. SAC2 is Sacramento River main stem between Sutter Steamboat Slough and Georgiana Slough. SAC3 goes from Georgiana Slough down to the confluence with Cache Slough, and then SAC4 is the remainder here. And there is also a Sutter Steamboat route, and there is a Georgiana Slough DCC route. The Delta Passage model has in it, and which is very important for the analysis that we're talking about this morning, far field effects. It has various flow survival relationships that were taken from different sources. On the Sacramento River side, the flow survival relationships in SAC1, SAC2, SAC3, SAC4, and Sutter Steamboat Slough were taken from Russell Perry's PhD thesis. Russell Perry actually looked at flow survival in the combination of SAC3 and SAC4, so that's from about Georgiana Slough down to Chips Island, as well as Sutter Steamboat Slough and SAC4. During the development of the Delta Passage model and the effects analysis for BDCP, it was felt that flow survival relationships would be reasonable to include for SAC1 and SAC2. It wasn't actually something that Russell did in his PhD. And so that similar sorts of relationships were established for SAC1 and SAC2, adjusting for the mean survivals that Russell had observed in his study. So there are flow survival relationships. Tricky to see the graphs here, but there are flow survival relationships. These are the flows, Sacramento River flows, and this is the survival proportion. And these are applied in the model on a daily basis for fish as they pass through these reaches. I just wanted to note that, as I mentioned before, SAC1 is, in the Delta Passage model, we are dealing with fairly broad reaches. SAC1 is the portion of the Delta Passage model that includes the North Delta intakes. Earlier versions of the model only accounted for the change in flow that would actually occur within that reach by changing the flow entering into SAC2. What we've done for the recent versions of the effects analysis is to try and account for the fact that flow would be changing below the intakes, and so we basically just took a weighted average of the intake locations, which are these river miles, consider where they are in relation to the start of SAC1, and then adjusted the flow. So, for example, if there was flow coming into SAC1 of 10,000 CFS with diversions of 2,000 CFS, and we just adjusted the amount of flow within SAC1. So that, in effect, gives a slight underestimate of the flow above the intakes, but it gives a slight overestimate of the flow below the intakes. Mostly what I'm doing this morning is outlining the methods, just because it's been of interest, I think, and agencies are seeking comment from the panel regarding the appropriateness of the methods. I won't dig into the results so much. I have a couple of example results, tables and graphs and things for these different analyses. But for the Delta Passage model, overall, the through Delta survival with the BDCP is in general similar to or slightly lower than existing biological conditions. And this shouldn't be a surprise given, and I'm talking about here, obviously from the perspective of the Sacramento River fish, which is our interest here in relation to the bypass flows and North Delta questions. It's a flow-driven model, so with diversions at the North Delta intakes, it can be expected that there would be, given the flow survival relationships in the model, that there would be less flow in the river and therefore less survival. tidal habitat restoration and other conservation measures are not considered in the model. Tidal habitat restoration only really manifests itself in terms of the effects that it might have on hydrodynamics, and as Chandra explained before, there are obviously some of those. For example, changes in flow splits at junctions, which I'll touch upon again a little bit later on. But overall, as I mentioned in the map showing the methods, the results reflect obviously the sort of different factors under BDCP, more Yola bypass access, Yola bypass being a relatively high survival route, more favorable south delta hydrodynamics for the portion of the fish from the Sacramento River that do enter the interior delta, and of course less Sacramento River flow below the North Delta intakes. We did do a sensitivity type analysis where we post-processed the results of the delta passage model to consider things that we felt we could fairly readily, based on existing studies, explore some of the different effects. So for example, non-physical barriers at Georgiana Slough, recent studies have suggested that those are somewhat effective at keeping fish out of Georgiana Slough, perhaps reducing the rate of entry by 2/3. So we explored that potential positive effect. We also explored the potential negative effect of predation at the North Delta intakes. So that would be the actual near-field predation effect. Obviously, the Delta Passage model generally reflecting the far-field flow survival relationships. Other conservation measures that might have potential effects, for example, CM6, which is channel margin enhancement, CM15, which is localized reduction of predatory fishes, those weren't explored with the Delta Passage model, just really because there weren't readily available values that could be explored with those. I think the next table is just an example of results. This is for winter run Chinook salmon, and this is comparing the EBC2 scenarios existing in late long term that Chandra outlined before to the evaluated starting operations BCP in the late long term. And as you can see here, as I mentioned, slightly lower overall through delta survival estimates from this model, again focusing mostly on flow-related effects. Within the appendix, so the previous table was actually from Chapter 5. This appendix here is from this table is from Appendix 5C, and this is just to illustrate part of a much larger table. I call it the big table. This is just a portion of it, and this is just to illustrate how we broke down some of the results to kind of give a pathway-specific perspective. So this one here is actually specific to individuals taking the main stem Sacramento River pathway, which includes the Verona Reach, SAC 1, SAC 2, SAC 3, and SAC 4. So the percentage of the individuals taking the pathway, and then their survival down the pathway. Were there any questions on the Delta Passage model, or?
Maybe you could refresh my memory a little bit. To what extent was the Delta Passage model derived from empirical observations, and how does the survival vary between sub-yearlings and yearlings?
So the Delta Passage model deals with smolt-sized fish, so that's taken to be fish that are 70 millimeters or greater. Most of the information in it is based on acoustic tag studies of late fall run fish that are essentially yearlings. That's a limitation of the model. Those are the best data that are available for those sizes of fish. Other portions of the model are there are other portions of the model that use non-acoustic tag. For example, the interior delta survival is a function of export flows. And is expressed. It's actually expressed as a ratio of interior delta survival to survival in the main stem Sacramento River. But it's mostly acoustic tag, especially the Yola bypass stuff was something new that came out. And again, it was acoustic tag, late fall run fish. Any other questions on Delta Passage model? No. So the second, one of the other techniques that was used in the river flow and survival effects was this juvenile spring run, fall run, Chinook salmon, smolt through delta survival. This was added in response to some agency comments on previous versions of the effects analysis based on Ken Newman's work. It's important to emphasize that this is just considering fish in the main stem Sacramento River based on capture of coated wire tag fish. And in this paper, through delta survival was assessed as a function of different covariates, including the size of the smolts, flow at Freeport, although for the effects analysis we used flow below the intakes just to capture the change in flow because of the North Delta intakes, salinity, temperature, South Delta exports, and turbidity. The graph down in the bottom left there is just to indicate the sort of partial effects of flow, which is the red line, and South Delta exports, which is the blue line. This is survival holding other covariates constant, and it's explored over the range of the covariates that Ken Newman used here just to illustrate the nature of those different relationships. As with the Delta Passage model, the results of this analysis suggested that through delta survival under BDCP was generally similar or slightly lower than existing biological conditions. Again, important to emphasize that this analysis is very much driven to looking at that particular issue of concern, which is how much might survival change below the North Delta intakes, largely because of flows. This does reflect both changes in the Sacramento River flows below the intakes, but also it considers South Delta export flows. The previous slide indicated that there is a fair amount of effect of export flows on survival, so that's also reflected in these results. It doesn't consider, obviously, yaw bypass effects, nor does it consider other effects such as habitat restoration or non-physical barriers or near-field predation. I mentioned some of those things were explored in the Delta Passage model. So it is important to realize that it's very focused on a particular subset of potential effects. A very new analysis that we added, again in response to agency interest, was what we call the North Delta diversion bypass flow effects on Chinook salmon smolt survival. This actually uses the same flow survival relationship from Russell Perry that had been applied in the Delta Passage model, which, just as a reminder, is the survival from the Sacramento River at Georgiana Slough to Chips Island. And this is actually based on the Sacramento River flow below Georgiana Slough. This was done for the full calcium simulation period, 1922 to 2003, based on daily disaggregated data. Backing up to Delta Passage model in Newman, those analyses were based on the DSM-2 simulation period, 1976 to 1991. So this was an analysis that was done over a broader period. But again, it's only looking at one particular aspect of the potential effect of flow over, in a subset of the plan area. It used the same daily weightings for Chinook salmon presence as the Delta Passage model. It was done for all of the different runs of Chinook salmon. And there was also an exploration of using an equal daily weighting for December to June. And then survival increment, so the overall survival was assessed in a given year, but then the survival increment, what I call the survival increment, which was essentially the survival proportion within a given flow level weighted by the proportion of fish that happened to be occurring during that flow level, was assessed. And so as Chandra mentioned before, there's 4 different sort of levels of bypass flow pulse protection: level 1, level 2, and level 3.
Excuse me.
Yes.
What fraction of the flows you simulated were within the range of Perry's data?
The question was what fraction of the flows were within the range of Perry's data.
Yes.
I don't recall offhand.
You don't know?
I don't recall offhand. But we can follow up and
Because that's obviously very important, since you only had 2 years of data.
Right. Yeah, and that's a general point. In some cases, or in a number of cases, there's likely to be extrapolation beyond the range of the data. So we should bear that in mind.
I think that would be important to include in the uncertainty factors.
This detailed table is just taken from Chapter 3, and it's really just to emphasize the point that Chandra made before, which is that there were pulse protection or bypass flow criteria applied. These are just examples for December to April period, as well as initial pulse protection. I won't go into the detail on that. That was just a reminder. This plot here, taken from Appendix 5C, essentially shows the survival under different bypass flow levels. So these are the pulse flows, these are level 1 flows, these are level 2, level 3, and then the overall. And those are comparing the BDCP's evaluated start in operations versus EBC2, and these are both late long-term. And so these are weighted by the proportion of fish that would occur. So you can see that a relatively low proportion would have been occurring during the pulse period here, whereas obviously there would have been more during this level 1 pumping. And basically the combination of all of these different levels adds up to the total survival. And so this was just a useful way of examining how the relative survival differed based on these different levels of bypass flows. This is for winter run Chinook salmon, and this is for spring run Chinook salmon. And this one actually illustrates the situation where under the BDCP's high outflow scenario, and where a species, and this is a spring run as I mentioned, where they overlap the spring period, which is when they were under the high outflow scenario, there would be higher flows than under existing biological conditions in wetter years. That the median, the overall message would be that the survival would be similar, or the median actually slightly greater because of higher survival in the higher flow years. Those last few slides were talking about river flows and survival relationships. As I mentioned, I was going to touch on entry into channel divergences as well, as that's an important topic. So for examining Georgiana Slough Delta Cross Channel, the same fish flow split relationship as the Delta Passage model was applied, which is what's illustrated in this graph here taken from Appendix 5C, which sort of shows the entrainment probability, entrainment being the probability of entering Georgiana Slough or Delta Cross Channel, being slightly greater than the fraction of discharge at lower discharges, and then less at the higher fraction of discharges. And this entry into channel divergences was also examined for Sutter and Steamboat Slough. There was no evidence of a relationship along these lines for that divergence, and so the fish split was assumed to be similar to the flow split. And this is all from DSM-2 data. A couple of example plots of the results. These are winter run Chinook salmon. Tricky to see. The main picture is here. The x-axis is the percentage of fish entering Georgiana Slough or Delta Cross Channel under the existing EBC2 scenarios versus under the BDCP scenario. So anything under the 1-to-1 line means that there's less fish entering Georgiana Slough under BDCP scenarios, and that's obviously the case under Georgiana Slough Delta Cross Channel. It was more variable at Sutter and Steamboat Sloughs. Just focusing on one that's easily observable, for example, the EBC2 versus Haas LLT high outflow scenario in the LLT. That's the red circles. You can see slightly higher at the lower discharges, so slightly less going into, slightly more going into Sutter and Steamboat Slough at lower values there, and around about the same at the higher values entering under EBC2 scenarios. So these results obviously reflect the DSM2 modelling. Were there any questions about the river flow survival from any of the models or entry into channel divergences? So I'll move on then to the last section of the presentation before lunch, which is dealing with restoration effects, which was another topic of interest. It's part of the review here in Phase 3. I'll touch on habitat restoration that was examined in Appendix 5E, looking at Foodweb benefits primarily, and outlining the analyses to do with that topic. Habitat suitability for covered fish species was also examined in that appendix. I won't touch on that today. And another topic of considerable interest was the effects of yawl bypass enhancement, which was examined in Appendix 5C. And I'll touch on an analysis of Chinook salmon fry growth, entry into the yawl bypass during migration for Chinook salmon, which is partly based on Delta Passage model as well as recent empirical estimates. The area of habitat for Sacramento splittail, and I won't talk about other qualitative analyses that were done, such as passage improvements at Fremont Weir for the sturgeon species, but those are found in the appendix and also mentioned in Chapter 5 of the effects analysis. Previous comments on the effects analysis noted that there was considerable emphasis on the function of tidal habitat for potential augmentation of the food web for open water fishes and for phytoplankton. And while we still think that that's potentially very important, we took to heart the comments to consider other aspects of the food web. And so as part of revisions to Appendix 5E, this food web conceptual model was put together here, and I won't go into all of the details regarding that. It is in Appendix 5E, but it's just to note that obviously the BDCP has considerable potential to affect important aspects that could affect the food web. For example, restoring much shallow water tidal habitat, obviously affecting bathymetry, could affect the relative areas of higher light conditions, and that could affect primary production. Obviously, the restoration of these relatively shallow waters can also boost the amount of emergent vegetation, for example, and these would then feed into different substrates for primary consumers, such as insects, that would then become food sources for covered fish species. I think the previous panel comments also emphasized the need to consider the detrital pathway. That's something that's been expanded upon in the public draft BCP in this appendix. Although the analysis remains qualitative in light of this conceptual model, as I'll show in the next couple of slides, our main sort of quantitative or semi-quantitative measure remains the consideration of habitat suitability, in essence, for phytoplankton, or prod acres as we were calling it. So if we would definitely be interested to hear any specific thoughts that the panel had on if they feel there's any other useful semi-quantitative measures that could be examined for some of these other pathways. As I mentioned before, our main semi-quantitative measure was this concept of production acres, which is I think production acres is a little bit of a misnomer. Our intent wasn't really to estimate or the extent of production that could change. It was really a measure of habitat suitability, if you like, for phytoplankton by extension, therefore things that could feed on phytoplankton. And so it was really looking at phytoplankton growth rate, which is this relationship here, as a measure of sort of habitat suitability in relation to depth. And then that was weighted by the amount of by the depth within the different areas. This is taken from Chapter 5. It was just a summary, just to emphasize that overall there would be this fairly appreciable increase in this measure, the broad acres measure, and that this would, depending on the area, so for example in the Karst Slough area, there would be a considerable increase, about a tripling of this measure. And in this analysis, and especially in Chapter 5, we do acknowledge the uncertainty in the availability of increased production and primary production and secondary production to covered fish species. Obviously, there's potential for consumption by clams, as shown in the recent work by Lucas and Thompson, as well as the extent to which covered fish species such as delta smelt may overlap with enhanced production from these shallow water areas. As far as yellow bypass enhancement effects,
quick question on the Foodweb. So the prod acre basis, is that sort of all area of restoration, so including shallow water as well as channels?
That's right. Yeah. So one of the earlier drafts, it may have been the last draft that the panel reviewed, didn't consider existing areas outside of the restoration opportunity areas. So a good example here is Sassoon Bay. No restoration proposed in Sassoon Bay, so essentially the same prod acres estimate.
But it's based entirely on depth, so there's no consideration of residence time or...
No, this is just an index based on depth, yeah. Were there any other questions? I kind of skipped on to yellow bypass enhancement, but were there any other questions relating to tidal? That was mostly focusing on tidal restoration. Okay, I'll move on to yellow bypass enhancement effects. The Chinook salmon fry growth analysis method that I mentioned before was, previously it was just for fall run Chinook salmon. In response to comments, we extended it to winter run Chinook salmon as well. Fish enter the plant area and have the potential to enter the yellow bypass based on a flow trigger. An entry into the yellow bypass is based on a flow split at Fremont Weir. The migration rate or residence time within the bypass or in the Sacramento River was dependent on size for fall run Chinook salmon, because they tend to be smaller fry, or date for winter run Chinook salmon, which tended to be larger fish. And the daily growth rates were set at 1% for the yellow bypass and 0.7%. That's body length based on work by Ted Summer et al. From 2001. Faster growth in the yellow bypass was only assumed at Fremont Weir spills greater than or equal to 3,000 CFS, which is the level at which the tow drain would overtop and the bypass itself would be inundated. And it was assumed, and this is I think an important assumption in the analysis, that the notch was open between December 1 to April 30th. Survival from yellow bypass to Chips Island is an important consideration in this analysis as well. The ultimate thing that the method gives is an index of ocean catch or ocean recovery of fish, although I should note that it should only be compared between scenarios rather than thinking about it in terms of an estimate of the actual number of fish. But part of this is part of the model is considering the relative differences in survival between Yellow Bypass and Chips Island. And so for fall run Chinook salmon, based on Ted Summer et al.'s work, the survival from Yellow Bypass to Chips Island was assumed to be 12.5% versus 8% for the Sacramento River main stem, those fish remaining in the main stem. For winter run Chinook salmon, there was a survival index in relation to length that was based on data from Fish and Wildlife Service that you see on this graph. Again, a figure from Appendix 5C. An important piece of this analysis, and really what the analysis was tailored towards, was considering what might the different survival be under different sizes of fish leaving Yellow Bypass or the main stem Sacramento River. And so a size-dependent ocean recovery rate was applied. This line represents the relationship that was used. And this seemed reasonably consistent with the different sources of data that were available. It was actually based on joining the points of shoals and halleck, but it seemed reasonably consistent with the other sources that were examined. This is an overview of the results, just looking at the results for all year. For fall run Chinook salmon, on average, there was about 14% greater ocean recovery rate, which ranged from about 2% more in critical years to about 20% more in wet years. Whereas for winter run, it was only a modest change, about 3%, 1 to 8%. At least part of this was due to the pulses occurring slightly before, the pulses of fish occurring slightly before the assumed operational period of the notch. And so I think that's something that obviously could be examined a little bit more, but that's one of the main reasons for that. The second topic I mentioned I was going to look at was entry into Yellow Bypass. So this is just looking at the proportion of fish coming into Yellow Bypass. This was looked at using results from the Delta Passage model, which assumes a fixed daily smolt downstream migration distribution based on historical data and then flow split entry into the bypass. And of interest was a recently available study by Jason Roberts and others that looked at actual empirical data from Knight's Landing rotary screw traps and estimated the proportion of fish that may have entered the bypass from the different runs of Chinook salmon. And this was looked at both under the existing conditions and the situation where there would have been a notch similar to the notch proposed under BDCP. These are example results for winter run Chinook salmon from the Delta Passage model. This suggested that there would be, on average, around about 4.5 to 5% under these existing biological conditions scenarios entering. This is the DSM-2 simulation period, 1976 to 1991. And that under the BDCP, these are a couple of the scenarios, evaluated starting operations and high outflow scenario, that it would be around about 12 to 13%. So slightly more than a doubling. These are the empirical estimates from Roberts et al. This is winter run Chinook salmon. They did the analysis over the 1997 to 2011 water years. The overall average was about 3% under existing conditions and about 12.5% with the notch. and those numbers differ depending on the water year type. So in the wetter water years, higher under existing conditions to about 6% and just under 16% with the notch. So these numbers seemed reasonably consistent with the numbers I just showed you here for the estimates from Delta Passage model. One other part of the considerations in the analysis was the recognition that not all of the juvenile Chinook salmon from the Sacramento River region would actually have the opportunity to benefit from the yellow bypass enhancement just because of the geographic location of where they would be spawned from. And so this analysis just examined the historic spawning escapement data to give a perspective on what proportion would be upstream, what proportion of tributaries containing spawners are upstream. So for winter run, obviously upper Sacramento River, 100%. This doesn't mean 100% of juveniles would enter the bypass, it just means 100% of the ESU would be upstream. For fall and late fall run, it would be about 50%, and this table here just illustrates the detail from Appendix 5C on the spring run Chinook salmon. So these various tributaries here, on average from the last 10 or so years, or 2002 to 2011, contributed about, on average, 35% of spawners, and all things being equal, perhaps juveniles, whereas about 65% come from Butte Creek. Now, it's not to say that these Butte Creek fish wouldn't get onto the yellow bypass, it's just that they may not benefit necessarily from the enhanced access to yellow bypass, because most of these fish would be coming out of the Sutter bypass, which is slightly downstream of the Fremont Weir. However, in years where there is a connection of Sutter bypass to Fremont Weir, and Yolo bypass, they could benefit from the greater duration of inundation of the bypass. Finally, talking about one of the other species that may benefit from Yolo bypasses is Sacramento splittail habitat area. This is an analysis based on primarily depth for spawning and early juvenile rearing. Velocity was also a consideration, but from velocity modeling, it turned out that the velocities would generally always be suitable, and so the analysis focused on depth. This is, as I say, habitat suitability. So, for example, from shallow waters 0 to 1.5 feet, that was regarded as optimal, and greater than 6.5 feet was assumed to be no value. This is based on field observations from Ted Summer and others on the Yolo bypass. Habitat was assumed to have value if it had at least 30 days of continuous inundation for the spawning and incubation period during February 1st to June the 30th. And so this just illustrates the appreciable increases that would potentially occur under those the notching of Fremont Weir under BDCP, these two bars here being evaluated starting operations scenario in the early and late long term, and differences between water year types, so these are averages. Again, taken from Appendix 5C. So I think that was all in relation to restoration effects. Yellow bypass enhancement effects. I don't know if there's any specific questions on those things, or
with more water going into yellow bypass, do you anticipate a predator response? More predators entering that area that might feed on the Chinook or the splittail?
Into the bypass itself, or it's possible. I guess you're meaning potentially avian predators as well as fish, or were you meaning mostly just fish? Or, I mean, it's possible, but I think in general,
predators that might offset some of the survival benefit.
Right. I think in general, it's been shown that the bypass is the higher survival location, and so it's better growth and so on. So it's anticipated that would be. It would be good. There may be some of that, but compared to the main stem Sacramento River, I think it's probably preferable. And I think, another thing I didn't really mention was that, oftentimes we're focused on this one measure. It might be through delta survival or something, but I think there's a lot to be said for the spreading out of the life history diversity, which we do try and discuss that a little bit more in the chapter 5, so that we shouldn't just think about what's the bottom line survival. We should also think about the fact that it's more diverse in terms of having more fish on the bypass versus more, in the main stem Sacramento River.
Is there data on what percent actually of the different runs actually access yellow bypass? In other words, independent of what's available in terms of the ESUs above yellow bypass, just what actually do access?
So, for example, in some fashion, tagging fish in their natal streams and then following them down, or
genetics?
Or genetics. I don't believe so. I think the results I showed there for these empirical estimates that were made by Roberts et al., those are based on length at date criteria. And so, I think those are some of the best estimates so far. I think
I was thinking basically a winter run versus fall late versus spring.
Mm-hmm. I think that's being looked at more and more. So I definitely anticipate over the next few years that sort of thing will be looked at a bit more.
Are there any additional questions from the panel on this portion of the presentation or the presentations you received so far this morning? If anything comes to mind. Okay.
There was one question that one of the panelists asked me that hopefully you can clarify real quickly. The restoration in the Napa River, is that included in the RMA modeling that is done for the 2D that would be driving the DSM-2 modeling? Do you know?
Red button.
So the model did extend all the way to...
I don't think it's on.
Okay. All right. This is better. So their model did extend all the way to Golden Gate when we were simulating the hydrodynamic changes. And I know that Napa River, part of it at least, was represented, but I'm not quite certain about the restoration itself on that. I have to get back to you on that.
All right. Any other questions from the panel about the presentations received thus far? All right. We're a little bit ahead of schedule here, but I think we will break for lunch and resume with the next set of BDCP effects analysis presentations, starting with the assessment of upstream effects after lunch. So we'll break now. It's 11:40, and we will resume back at 1 o'clock. Thank you.